give everyone an idea of the basics of electrical engineering, as it were. We're going to talk a little bit about electricity because it's important that you understand the way that these systems are put together so that when we talk about failure mechanisms, they'll make a little bit more sense to you. We're going to talk about the connections involved in PV systems and specifically the number of connections that are involved in a PV system. We're going to talk a little bit about what we call the gold rush in facts of the industry growth. Now, I'm in Canada, and our gold rush of the PV building hit about 6 or 7 years ago. Um, it's going to be a little skewed to the Canadian side of things, but the physics and everything will still be the same. Um, I'm going to talk a little bit now after that about the darker side of sunlight, and we're going to start talking about failure mechanisms and what happens and why they do happen. Um, but we then we're going to talk a little bit about quality assurance, quality control, and the commissioning process that's involved in getting these systems up and running. And then towards the end, we're going to talk about some geotechnical issues that are more specific to uh, hot and cold climates with solar farms. And then I'm going to give you a bunch of issues for consideration. Now, I know that I've got a very large cross section of people here. I believe right now we've got 630 of you online, and we're going to go up above the 850 mark. So we do have a lot of cross section of different peoples uh, from the adjusting side of things to the loss consideration side of things. We're going to try and talk about a little bit of the pre-loss and the post-loss side of the solar world as we know it. Um, I think what we're going to do is we're going to start talking a little bit solar panels, and as you can see from the picture, this is just a typical small commercial rooftop. Um, so ultimately, to start with things, actually, I'm going to step back for one more second here. Um, I, I just want to let everyone know that when I start this, that this is basically a basic overview of what we're going to be talking about. So we're going to talk about basic layouts of systems, basic sizes. We're going to talk about some big systems. And I also want you to know that my background is not in electrical engineering, but my background is in fire. I am a fire scientist, and if you think there is a relationship between solar and fire, then you've pretty much got it correct. And this ultimately is how I got involved in solar. So let's get started, and we'll talk about photovoltaic systems. Um, Ultimately, in its simplest form, without going into the high-end physics of things, we have sunlight. The sunlight is going to hit a solar panel. The solar panel is basically going to generate an output of voltage and amperage, so we're going to get a current flow out of the panel. And in its simplest forms, which is a lot of what we're going to deal with today, that's just what we have to remember. Um, the most interesting type about solar, though, is that we have a couple of types. Um, so if you remember our plan earlier, where we have the sunlight coming out and the sunlight creates power, we have a couple of different types of solar, though. We have a method called concentrated solar power, or what we call CSP, which is an indirect type of lighting. And we have another one which is called photovoltaic, which is a direct type. And this is the most common one that we're seeing installed today. The concentrated solar power systems um, tend to look something like this. They're like something out of a fancy science fiction movie, and they can get quite large. So in this photograph, you'll see one method of concentrated solar power, which is basically a massive field with a huge number of mirrors that will track the sun, and they'll focus them onto a tower. Now, what we're doing here is we're actually focusing this sunlight onto a tower. We're generating heat in a water-based system, and it's basically a steam turbine. So the concentrated solar power system is different in the operation of the PV system in that method. They do get quite large. Um, as you can see here, this is in the Arizona desert, and we're looking at massive amounts of systems here for concentrating, and you can see the three different concentration towers in the top of each one. This is a secondary style of concentrated solar power, and what we're looking at here is, if I can grab a arrow here, the mirror system here is picking up the sunlight that comes down from above, and it focuses it on this rod that runs all the way through the center of here. And what we have here is we're basically piping a water-based or a coolant-based system through here that gets very, very hot. And again, we are running this into a steam turbine system, and basically not much different than solar would be. We're just generating a lot of heat and power, and we're spinning a turbine with it. So this is just a little bit different. And again, these systems here are can get quite large, and you'll see the size of the mirror here in this one. It goes from here to here, and we've got some people here, and the concentrated piping runs right through the center of this system here. And when we stack them up, they can be rather large. So we can create an enormous amount of energy with these systems. And where we're seeing them being built is in the middle of nowhere. We've got scrub land that's in the middle of a desert, and there's no better place to create generated power than in land you can't otherwise use. Now, there is a cost associated with that because it's great to have all this power here, but you've got to get it somewhere. Sorry, all this power here, but then you've got to get it somewhere. So now you've got lines and systems and infrastructure that you have to build to get it out. But again, this is the concentrated solar power system. What we're going to talk today, and I'm going to focus more on this, is we're going to talk more about photovoltaic power systems. Basically, the photovoltaic power system, like we talked about in our earlier slide, is that we're going to take electrical energy from these panels here, and we're going to drive it down to some kind of power line through some kind of inverter, and we're going to create electricity that we can use in common place without having to boil water and spin turbines. We're creating direct current with these panels here. Now, you're looking at a typical residential system here. This is larger than most of the residentials, and I don't know what it's like where you are all living right now. But I know living in Toronto here, there's a push, and people will be putting 6 or 8 or 10 of these panels on their garages in the back of their house, and trying to create a small amount of energy, just to try to offset the enormous kind of energy costs that we're seeing, especially here in Ontario right now. So I want to get some terms across right now so that as we start to build on this, that I don't start talking slang to everyone. Um, Fundamentally, a solar panel, or what they call a module, is made up of a series of cells. So you can see in this panel, we've got cells that are 4 wide by X number tall. So these many cells create a panel. Most industrial cells or commercial cells that we see, or panel modules that we see nowadays, usually have about 72 cells in one module. When you put a series of modules together, um, like we see one module here with a bunch of modules here, this is what we call a solar array. So when you see a whole bunch of solar cells that are placed together, it's what we call a solar array. Now I'm going to build on this model that we see here a little bit later, but for the fact now, all we really need to know is that we have a cell that is placed into a module, which is a multiple number of cells, and an array, which is a multiple number of modules. So if you have any questions, like I say, feel free, just dump them in the question and answer column here. I'll jump in and answer them as I can, but we're going to continue. So when we start looking at solar array systems, if you all remember the small residential system, um, uh, sorry, and I have a question here that I need to quickly address. If you have more than one module, the question here is, was that 8 or 10 modules on a residential installation, or is that an array? Basically and fundamentally, if you have more than one module and they're connected together, that's an array. Now, an array can have um, 2 to 100,000 different modules in it, so or they can be quite large. And you're looking at a solar array on a large commercial building right here. Um, this is not a large one, but we're looking in the neighborhood here of a 1 megawatt installation. And in this 1 megawatt installation, we have about 5,000 modules. All right. So, and Brian has a question for me right now about the Tesla roof system. Brian, we're not going to talk about that, but I'll gladly talk to that after this offline to help you with that question. Um, so to continue, um, what we're looking at here now, this is a 10 megawatt solar solar array, and as you can see, this one's taken from a long way up. In this one here, you're looking at about slightly under 60,000 modules. So we can keep expanding these and expanding these and expanding these infinitum, depending on the space that you have and the ground space that you have and the capability of getting the power out of this place back to some kind of metropolis that can use it. So this one is quite large in its neighborhood. So I want to talk a little bit about what we talk about. And I know I'm using these terms like kilowatts and megawatts and gigawatts. To put it into perspective, a residential system that you saw earlier, which is 8 to 10 modules, sometimes you see 8 to 16 modules, at its best day might generate 2, maybe 5 kilowatts of power. So to put that into perspective of how much power that actually is, 1 kilowatt will generate enough power to run about 60 normal style incandescent or LED light bulbs. Now, in a nutshell, basically incandescent. Let's not talk about LED at this stage, but it'll generate about it'll have enough power to generate to run about 60 of them. Or in better speak, you could run about two 24-inch computer monitors, or if you had a small pool pump and one of the Flowtech small ones, you might be able to run that this small pump in itself here. So, and that's about what takes 1 kilowatt. Now, the interesting thing to remember, though, is solar panels or PV panels require a fair amount of light energy in order to be fully productive. So, in other words, at 7 o'clock in the morning, and we all know what it's like when we walk out first thing in the morning and we go, oh, it's a beautiful, calm, and cool day. And the light, because the light's coming down on a nice angle towards us. The thing about solar panels is they look at it the same way. So the solar panel will see this light coming in on it. It'll generate a small amount of energy. And then at 8 o'clock, as the sun comes a little bit higher and directs itself this way, so it will come down that way. And then as the sun gets higher, it will generate more energy and more energy and more energy and more energy to a peak of the day where it will eventually have enough energy to generate about, its 1 kilowatt range. But as the sun now gets across the sky and starts to set, you'll see that the energy has a tendency here to start to drop. So I have a point here about the microphone being, someone can't hear me. So Seth, if you could have a look at that. So ultimately, As the sun rises, the energy goes up, the output energy from the array goes up, and as we start to descend here towards the later part of the day, the energy starts to stop. So ultimately, midday is where we make most of our energy. And we're going to talk a little bit about that in a little second here. So um, as we move on, so the interesting thing about solar is a function about the amount of energy that we can get out of the sun. So if we have a bright sunny day where the sun is directly striking one of our PV modules, we can generate approximately 1,000 or the sun will generate approximately 1,000 watts per meter squared. I'm not going to get too far into this, but this is a function of energy, and this is a large amount of energy. The problem with solar, the problem with the whole function of it is if we get a cloud that rolls across the sun, we can go from 1,000 watts per meter squared to 300 watts per meter squared in less than a second. So in in this understanding, you can see that we have a lot of energy, and in less than a second, we have very little energy being produced. So, in the same standpoint, in this 1,000 watts per meter squared, all of our cables and all of our wires will heat up because we're starting to flow a lot of energy through them, and then they cool down, and then they heat up and they cool down. So as it gets to be a more cloudy day, if the cloud rolls through, then the amount of energy output by the solar array drops as well. Um, and if we have a completely cloudy day, we will get very little energy out of that thing, even in the midday. So solar, the amount of energy that we output from a solar array is a function of how much sun we hit it with. Um, also, so it's much the same as earlier on in the day, even on a sunny day, because the sun doesn't hit the solar panel directly, we don't get a lot of energy. Well, the same function applies when you have a cloudy day. We don't get the direct amount of sun strike, and we don't get the direct amount of energy that we normally would. Consequently, if you're living, for example, here in Toronto in the middle of the winter, we just don't get a lot of sunny days. So the efficiency of your solar array is very small. Summertime, sure, we get some great amount of solar power. Um, moving on. So as I talked about earlier, yeah, we get very little energy out of our morning section, and then we try to peak out here around the afternoon or noonish, assuming that the sun is high noon. And as we start to drop down in this method here, so we make a little bit of energy, we make a little bit of energy, and then we make a lot of energy, and then we make a little bit of energy. What most of the energy producers are doing nowadays is they're saying, well, wait a second now. Um, uh, what if I were to increase the number of modules I had um, so that I would start to generate more power in the morning? So what they do, so in example, let's just say for a moment that one panel generates 250 watts of output power. We're going to talk about basic electricity in a minute. Um, so if we had 4 panels, we would generate 1 kilowatt at its high peak time when the sun strikes it the hardest. So what would happen if we put 5 panels in there? Okay, we're going to generate 1.25 kilowatts at our peak power. But what happens to the whole graph is that we start to generate more power, more power, more power, and more power. And you can see that there's a radical increase in power starting in the morning, moving up, and then moving back down. Now, there's an issue with this, because otherwise someone would say, well, why don't we put 50 panels in? The problem is that the output energy, it becomes a function of what the system can output. And that is we're feeding this energy to what we call an inverter. And an inverter can only output so much energy. So what the inverter does, it says, I'm sorry, I can only output this much. So I'm just going to clip this off and not send it out. But you can see that we're getting a higher output on each one of these. Now, in theory, I know that in Toronto, this varies from place to place, but in Toronto, they have a tendency to overbuild by about 30%. So if they're looking for 1 kilowatt output, they will target 1.3 kilowatt output, so that they're just going to add more panels and more panels until they can get that mathematical calculation. And there's all kinds of algorithms that they use to figure this out, but ultimately this is what they call overbuild. So you will rarely find a industrial commercial build that does not involve what they call an overbuild, because in the cloudier days they want to be able to generate more power, and this is what they do. So I have a question from someone that says, "Isn't there a way to store energy on bright days?" Um, yes, there are several ways to store energy on bright days, and this is something that, especially in Canada, well, North America proper, is I know we think we've had them for a long time, but this is, we're storing them in batteries, we're storing them in water towers. We're storing energy in many different ways. Um, that that is a whole other seminar that I will be talking about, and it's not part of this one, but we do have a storage seminar that we're going to bring online in about 6 months. So great question, but I hope that answers it for you. So anyways, to continue here. Um, I'm going to show you quickly. This is what a little residential grid connected system looks like. And we'll talk about the grid in a minute. Ultimately, we have people at home, and what they do is they put solar panels on the roof. Um, and the solar panel comes down to an inverter. And basically, what an inverter does is it takes the direct current that's generated from the solar panels. And by direct current, I mean the same as a battery, and it changes it here to alternating current, which is what we use in our right here in the which is what we use in our house to drive our TVs and our lights and our washers and dryers, etc. So these panels come down from DC, they get changed to AC, and they go into the house. Now, the question is, well, what if I don't need all that power that's generated? Well, that's fine. What happens is, instead, if you don't need it to go into your house this way, that will now go back through your meter, and it will connect up to the utility service, and your Hydro Toronto, Hydro Las Vegas, Hydro whomever will take that power and they will use it. And interestingly enough, your meter spins the other way, or there's another meter here that measures what's going out to the grid, and you get a discount or a credit on the amount of money that you've paid for your electricity. Usually in residential, that's not a huge amount, although during the day when no one's home, if that thing is spinning, then you will get some kind of credit on that. And the credit per kilowatt hour is so variable, it's phenomenal. Now in Canada, about 6 months ago, the government decided that they were going to introduce a feed-in tariff program and offered an enormous amount of money for the amount of money for the amount of power that we could send up to the grid. And people spent billions of dollars building systems. We're going to talk about that when we talk about the gold rush in just a little bit. I have another question about how efficient these panels are. These panels themselves, and this is an interesting point. I would say generally about 20% of the energy that hits this panel makes its way to this inverter box. Uh, Solar panels are extremely inefficient right now, although we are seeing much greater efficiencies. And the person that talked about the Tesla system, the Tesla efficiencies is higher than our standard PV modules that we're seeing now. Leave it to Tesla. So to continue, when we look at a commercial rooftop system, a commercial rooftop, or I'm going to call them like a medium rooftop, and these are the kind of commercial systems that we'll see on the roof of a Home Depot or a Lowe's or a big box store. These run in the neighborhood of roughly about 2,000 modules. and in these modules, you'll generate about 500 kilowatts or 1/2 megawatt of power. So this is an enormous amount of power. Um, there seems to be for years this fallacy that solar is such a safe thing, and I've got a solar calculator on my desk, and you know, I've never had a problem with that. But when we start to connect these things together, and we have 500 kilowatts of energy, these things generate an enormous amount of energy. This is basically a propane generation plant sitting on the roof of Home Depot. Um, so this is a very large amount of energy that is generated by these systems, and these are not overly large ones at that. So this is a typical big box store. You know, you're looking in the neighborhood on this one. This one's a little bit larger because this is a 1 megawatt rooftop. So it has this one I know well, and this one has about 4,500 modules on the top. So to move forward, if you look at the way that a commercial rooftop system is built compared to that we saw in the residential system, where the residential system grabbed power, went down to an inverter, and then basically went either up to the grid or into the house. The commercial systems are a little bit different because they're so large. So what they will do in a commercial system is they will take so many panels, put them together, and put them in a box. And then they'll grab a bunch more panels, connect them all together, and put them in a box. And then they'll combine this box and bring it down to here. And then from here it goes to our inverter that changes the DC to the AC, and then it'll go to a transformer, and it'll either step it up or step it down and go off to the grid. Um, there are some of our larger commercial systems. I know that a lot of Home Depots will take the power and they'll run it into their own store first. In the extra, they will run out and head it to the grid. One of the issues that we have, at least in Ontario, is that there are a lot of companies that run around now and they will lease your rooftop from you. So every month, you know, you have this rooftop doing nothing. They will put a solar array on it. It won't charge you anything for putting the solar array on it. And then they will just take all the energy that's generated on the rooftop. They'll run it down through a combiner, through an inverter. They'll go through a meter, out through a transformer, and off to the grid. And they will take all this money. And then once a month, they will send you a check for X number of dollars, and and that's fine. The issue with this is these panels here. What if there is a fire? So we have a fire on a rooftop that's leased out by space, and we burn through the roof, and we dump, you know, the byproducts of combustion down into the store. So these are issues that, as a fire investigator and a fire scientist, and this is how I got involved in this industry, was that same thing. We had a fire on a rooftop, it burned a hole through the roof, and down came the fire into the store. So there's all kinds of legal ramifications. There's all kinds of insurance-related ramifications involved in that actual system. Um, and we'll talk a little bit more about that when we get into what we call the gold rush. Um, to continue, when we look a little bit further in a larger production-based systems, we talk about ground mount solar systems, or what we call a solar farm. These systems are very large. They generally run in the 40,000 module range, and they will generate in the neighborhood of 10 megawatts. Now, here in Toronto, just west of Toronto, up on top of the Niagara Escarpment, they've just built one that's just over 100 megawatts, and there's 400,000 modules involved in this system. So these are now massive generating plants that create an enormous amount of energy. Um, so if we start looking at solar farms, like this small solar farm here, what we're looking at here is a farm that's only 5 megawatts, and you can actually see the true size of these systems here. And in retrospect, when you look at the size of them, the amount of energy that's output, When something goes wrong with them with that amount of energy, it's basically like a large propane plant having a massive failure. So the destruction is enormous. So we're going to talk a little bit about destruction, and I'm going to move along here because I have a tendency to yak a little bit. But we're going to talk a little bit about electricity. I want everyone to understand that when we talk about units and measurement, we're going to talk about voltage, we're going to talk about current, and we're going to talk about power. Um, we're going to talk about types of electricity. We're going to talk about direct current, like we were talking about, that comes from a power. We're going to talk about alternating current, which is what we usually use in our homes. And I'm going to talk about connections. I'm going to talk about what a series connection is, and I'm going to talk about what a parallel connection is. Because in order to understand the way that PV systems go together, you need to understand these terms. So to put it into a more simple comparison, uh, it's easier for me to describe it to people when we talk about water versus electricity. Because when we talk about water and we talk about pressure, we know that if we have a pump that pumps water, we get high pressure that comes out, and as the pressure starts to diminish, it becomes low pressure, and then if we put it back into the pump, it goes high again like this. So if we look at current, it's not much different. If we have a battery and we send high voltage out to some kind of load like a light, the voltage has a tendency it wants to drop and it comes back to the battery again. So we have a positive side and we have a negative side to a battery. And if we look at it this way, so in another term, if we really look at um, voltage, which we talked about here, or pressure, times current, which is flow, it equals power. So if we have a lot of pressure and a lot of flow, like a fire hose, we have a lot of energy coming out of a fire hose. The same applies to electricity. If we have a lot of voltage and a lot of current, we have a lot of energy coming out of our power cord or our conductor, whatever that may be. And what is power? Power is the rate at which work is performed, and that's just a fancy term for what we call watts. So if we have a 60-watt light bulb, that is the amount of power that is generated or the work that is performed by that light bulb. So to put it into perspective, again, the interesting thing, we're talking about direct current, and we all just know what a battery is. And I had to take the name off this battery because the legal people didn't like it, but I'm sure we all know the color of this battery. This battery has a positive side and a negative side, and anyone that's ever put batteries in a flashlight always know why it doesn't work is because we always put it in the wrong way or we put them the wrong way together. So a positive, negative, and let's just assume for the sake of argument in this conversation here that our power is going to go from the positive side back to the negative side, just like that. We also have alternating current, which is what we see in our house. And in alternating current, we have a hot conductor, a neutral conductor, and a ground conductor. So most of our cabling of our house basically has a hot, it has a neutral, and it has a ground. We have a hot, a neutral, and a ground pin on most of our three-prong plugs, and this is what they is. And alternating current basically goes one way and then goes back the next. So it goes one way and then back the next. Um, so if we talk about a series connection, which is what we're seeing in this place, we've got one battery, and another battery. If I want to connect these batteries together in series, what I would do is I would connect the positive side, the negative side to the positive side, the negative side to the positive side to the negative side. So I've got three batteries connected here in series. So when we connect them to series, it looks like this. So when we connect something together in series, we take the voltage of each battery and we add them together. So in this case, we would have this battery voltage and this battery voltage and this battery voltage, and I'll get to that in a sec. And we take the current output, which is how much power we get or how much flow we get out of each battery, and it's the same. It doesn't change. In a parallel connection, it's a little bit different. In a parallel connection, we take the positive, we connect it to the positive, we connect it to the positive, and then we take the negative, we connect it to the negative, and we connect it to the negative. So the positive side and the negative side. The difference here is the voltage connecting these together doesn't change, but the amount of energy that we create does change. Basically, we're making just one great big battery when you connect it in parallel when we do this. So let's put some math to that and it may make a bit more sense. So if our battery creates 1.5 volts and it is 1 amp, and we connect them all together, what we're going to wind up, we know that voltage plus voltage, so we have 1.5 plus 1.5 plus 1.5, like this, it's 4.5. And we know that the current output doesn't change when we have a series connection. So in this case, we have 4.5 volts and 1 amp. And this will make a lot more sense when we start showing you on a panel. In a parallel connection, we know that voltage doesn't change, but the amperage changes. So in this case, in a parallel connection, we see 1.5 volts because we know that we connect all the positives together, and we see 1 plus 1 plus 1. So we have 3 here. So 1.5 volts and 3 amps. So this is the difference between a series connection, and I always like to say series equals sum. So you sum 1, 1, 5, or 1, 5, 1, 5, 1, 5, and you get 4.5. So, and when we change this now and we look at this in the terms of a bunch of batteries that are connected together in series like this, it's the same as a bunch of modules from here to here, all connected the same way. So basically on a module, you have a positive and negative side. So when we connect them together, we connect the positive side. So we go into the positive, out the negative to the positive, negative to the positive, and so forth. And we go all the way through here. So it's no different connecting solar panels this way in series than it is connecting batteries. So think of a module as a battery, and you're connecting them all in series. All right, interesting term now. When we connect a whole series of panels together, we have what's called a string. So when you see a string of panels, or you hear them talk about a string, this is what they are. They're all connected together like the same as connecting these batteries together. So we talked about this chart before, and I said I was going to add to it. So what I'm going to add here is that in this case, here's our cell. We know it's part of a module. Now when we connect a bunch of modules together in this method in series, this is called a string. And then we take this string and in the series of an array is basically a whole bunch of strings. So we've added one term in the middle. So we've got a module, bunch of modules equals an array. Now we know that a series of strings are within the array. Now what the strings are, this is the way that we up the voltage, because remember we talked that a series connection between two batteries ups the voltage. So we want to have enough panels connected together that we create a certain voltage, and they add panels to output a voltage that they're looking for. Now in Canada, our numbers are a little bit different. Generally, we like to see either 600 or 1000 volts by a string of panels output. So if you do the math, that most panels, a 72 cell panel will generate approximately 30 volts when you've got great sunlight. You can see how many panels we have to put together in order to make a string that'll output 600. So roughly, you're looking in that neighborhood, mathematically to do that. And when you have 1,000 volts output from a string, you need even more panels to accomplish that. Okay, moving on, speeding up and moving on. So in this case, this is a small array on a rooftop. We talked about the way that we connect these. We connect this panel all together like this as we add them all together. So in this case, we know that a panel will generate 30 volts and it's about 8 amps output. So it's like our battery. Our battery generated 1.5 volts and output 1 amp. These panels generate 30 volts and output 8 amps. So we've got a bunch of panels here. So what we've got is we've got 16 panels or modules, which equals 480 volts at 8 amps, because these panels are all connected together in series. So in series, we know that the amperage doesn't change, only the voltage changes. So you can see now this is a lot of energy. 480 volts is a lot of power that's generated by 16 modules themselves. The interesting thing about this is, for example, if we had a neighborhood that was all connected together, we had a house here and the house next door was generating 480 volts, and the house next door was generating 480 volts at 8 amps. When we connect your house, your neighbor's house, and your other neighbor's house together, um, they still eat. When we connect them this to this to this is a parallel connection. So now we have 480 volts, but we have 24 amps, right? And we know that when we take amperage and voltage together and get power, we have an enormous amount of wattage that's generated just by these rooftops. The interesting thing about this math is that these are just small 16 module things. When you start generating power and you've got 40,000 modules, you can see the amount of energy that comes out from these systems. So to continue, um, so this is a string, and we talked about the way they connect on a rooftop. These strings all connect in what we call a combiner box, and each one of these red cables that you see connected up here is a string. So all of these strings connect together, and the power from this box goes out. So we also have another string series that goes in here, and each one of these red ones is a string of power. Each one of these red ones is a string of power. And now they connect together in what we call, and they connect together in this box. So this combiner box goes to this box, and this one goes to here. And then we have another one going here, and another one going here, and another one here, and here, and here, and here. So there is an enormous amount of energy here. Now, this energy here goes to an inverter. This inverter takes this DC power and it changes it to AC power. It sends it out to a transformer, and the transformer sends it up to the grid. Now, there's a lot of systems in between here and in between here to measure the power to make sure that it's fit to go up to the grid. There's metering systems here, and there's switch disconnects, for safety, and there's fuses. But in its basic form, this is a solar array. It goes from here, it gets combined in here. These strings all combine in here in what we call a string combiner. The string combiner goes to an array, or what they call an array combiner, and they're all combined here to an inverter, to there, to the grid. So again, in its simplest, power to the strings, to the string combiner, to the array combiner, to the inverter. These are the disconnect switches to allow you to disconnect from the grid. This is all part of electrical safety code. Into metering cabinets, into fuse systems, into the building power, to the transfer to the grid. So these are the boxes I said that fell in between. And again, there's numerous setups for this going on here, which is why I basically just touch on it. It's a whole course into itself. So obviously, this is what a panel looks like. We talked about our panels here, all connected in series. The connection point on the back of the panel here looks like this. So this is the power in and the power out. So there's a positive and a negative side to each panel, just like a battery, because it is DC. And all the wires coming off the arrays travel through this tray of cable. As you can see, there is a lot of cabling. This is what we called our string combiner box. Each one of these red cables represents a string. In this case, this was a 1,000 volt panel. So there's 1,000 volts coming off each one of these red strings. It's all connected in parallel here, and these are fuses along here. Though that last panel we saw comes down into here, and it connects to this fuse, or rather breaker. Each one of these represents a breaker. These little blue things measure the amount of current coming in, and they all connect now down in this system here in parallel. So this is a huge amount of parallel energy, and you can see the size of the cabling that the output cable uses. This massive cable up here, they come in small, but because we combine them all together, they go out very large. So the inverter system itself, I'm sure that everyone has used something like this. I have one in my car, and I use it to charge my laptop or my cell phone. It basically plugs into your cigarette lighter, and it generates 120 volts output. You know, it doesn't generate a lot of power. This one only generates 40 watts. Um, these are bigger commercial systems here. This one will generate 250,000 watts output, so it takes the power coming in, and it will output AC. Um, and then there's several different types, and they're made all over the world. These again are just different models of inverter systems, right down to very large systems. So we have the DC side coming in here, the inverter system happening in this system here, and its output side here out to the grid. Again, these are just simple metering cabinets. We've got power on the AC side coming to switch disconnects. This allows you to disconnect the system through a meter bank and then back out again. This goes out to the grid. Actually, this one goes out to the transformer system here. And the transformer looks simply like this. So for the sake of speed here, we're going to run through a little bit. We're going to talk a little bit about why solar has become so popular. Obviously, the big green kick has come along. I don't know what most of the places you live in, but in Ontario, we had what we called the gold rush, and it was just like the gold rush of old. Anyone that could do anything ran out and started to pan for gold. Well, the same thing happened in Canada here, especially in Ontario, and we came in with this feed-in tariff program. Um, uh, there was very little codified information when we first started getting into solar. There was a lack of familiarity with DC power. Most system designers had no idea what they were doing when they were designing them. There was no standardized training for installers, and there was very few codes involved for the PV installations themselves. We had systems that were rapidly designed and that were massive in size, and there was absolutely no quality assurance or quality control programs in place. Consequently, we saw all kinds of installation deficiencies. We ran into and we were putting systems on roofs that were supposedly going to last 20 years. But the problem is we were building them on roofs that had rooftops that only had a lifespan of about 3 or 4 years. So that then now we're ripping all these systems off to put new roofs on. There was this mentality that you just put these things up and you set them and you forget them. Unfortunately, the issue that we have is that the set and forget mentality, these systems are breaking down. These systems were rarely monitored, serviced, or commissioned or recommissioned. They basically put them up there, and now they're failing, and they're failing in catastrophic ways. Thus, the fire investigation side of me. There was what we're seeing now is systemic mechanical and electrical fail mechanisms on the earlier what they call legacy systems. And when you've got a 5-year-old system and you're calling it legacy, you knew that there was an issue. There's an issue with the way that they were initially installed. So, and again, the utility infrastructure is outpaced by growth. And the example I use is in Western Ontario towards the Windsor-Sarnia group. Although not PV, we put hundreds of wind turbines in. We had the wind turbines installed, and they were standing there with the plug at the end of the wind turbine, and the Ontario Hydro had nowhere to plug these things in. So we had all of these wind turbines and nowhere to send the power. So we have rapidly tried to catch up in our infrastructure to catch up with the growth. Talking a little bit about the growth quickly, and I know that I'm running out of time here, but quickly you can see this is USA numbers here, and you can see between 2015 and 2016, we doubled the amount of photovoltaic installations, and these are in megawatts. So you have about 7,000 megawatts more between 2015 and 2016. Interestingly enough, globally, you can see 2014 and 2015 here. You can see a large amount in that same curve. More of an exponential curve went up the same in 2016, and I'm sorry I don't have that slide for you, but you can see the trend of the way this is happening. So we're going to talk a little bit about the darker side of sunlight, and I'm briefly just going to run through some of the issues that we do see in the world of PV, and the way that the quality control systems are very important. We have a lot of people that install these. They look at them and they say they're fine. But you have to remember that in a 500 kilowatt system, there's more than 2,000 panels. And roughly over an average of 2,000 panels, there's 2.5 connections per panel. And in the world of electricity, most of your failures occur at connections. So when you've got 2.5 connections per panel on a rooftop of Home Depot, you have 5,000 potential failure points in a system like this. It's hard to see until you start looking at this. When we shoot this thing with an IR camera, we start to see this system. And in what we have here, we're looking specifically at an overheated connection. You can't see it with a naked eye. So if your installers aren't using these kind of systems, these kind of problems here will eventually overheat, and this is where we start to see our fires occur. So if you look at the old way of doing it, commissioning was considered synonymous with, with quality control. So in the old days, what they used to say is, well, quality control is a performance metric. So in other words, they put this thing on the rooftop, they make sure everything was connected, they go downstairs, they turn it on, and they say, see, I've got all this energy coming out, so it must be working fine. Unfortunately, that just doesn't work. Performance is not an indicator of quality nor longevity in a system. Quality assurance systems that are being done now by the more reputable people is that they design they design their systems to a predetermined standard code or performance metric. And there's a safety measure and a certain lifespan. And the quality control that is done before these things turn on is to make sure that their system fits that quality assurance program that they've developed. And really quickly, this is some data that we've done. I've done investigations in over 250 megawatts of energy systems now. And these are, I just want to give you a list of our top 150 rooftops that we did visit. And I'm gonna start to. I'll just give you a list of the top nastiest problems that we do see that develop these kind of common failures. So ultimately, quality of workmanship is usually our number one. Loose connections, we see improper grounding, unbalanced strings. In other words, one string has 14 panels, another one has 20 because they've made a mistake. We see reverse polarity where they connect the negative to the positive and the positive to the negative. Transformer mismatches. Roofing issues. It's not uncommon to see them screw these things down into a roofing membrane. So the next morning after a rain, the store is filled with water. We see the modules being damaged as they're transported up to the roof, and numerous types of electrical failures. This is the number 5 problem. We see code violations in this. We see people connecting multiple wires into a ground screw, and we exceed the current rating. We see it in numerous conditions. This is actually in a metering cabinet here. Our number 4 is we see a lot of cables that are just laying on rooftops. So as it gets wet, these cables become submerged. The right picture here that we see, this is a proper way of doing it where they're all elevated off the rooftop itself. The number 3 problem that we see lack of labels on anything. We don't know what is what. This one isn't labeled too bad. The problem with this one was there wasn't even a door on this panel when we went to the rooftop to look at. They took it off to do some connections and they left it off. Our number 2 problem is our hotspots that are identified by IR cameras. We find numerous hotspots. And the hotspots are basically elevated temperature caused by loose connections, caused by unbalance. And we actually see panel hotspots in themselves. So this could be a damaged panel as it's being brought up, or it could be a panel that was damaged originally from the manufacturer. And the number one problem that we find, the number one problem, is that we have under torque lugs. And we can see them, you can see where they're actually under torqued, the wires that go in. And what happens is because they're loose, we start to get a loose connection, an electrical loose connection. And these are found, so many times. It's amazing. The problem is when you do a physical inspection, they look like this. After a physical inspection, however, it's important that you can physically inspect it all you want, but unless you shoot it with a camera, you're not going to find out that we do have an actual issue with this. So if you look at that connection, you'll see it looks like this. And if you look at it further, you're going to see that it connects like this. So we have an issue here. So ultimately, most of the time that we spend looking at our failures, the IR camera is our number one tool. And you have to remember that when you look at these systems, um, when you're going to examine these systems in the world of failure mechanisms, that when you're up on a rooftop and you're looking at a solar system, that when there's sunlight, they will create power. Even in the moonlight, they will create power. And when you turn the power off on the ground, these systems will still generate power. So ultimately, I just wanted to give you an overview of how they go together. I wanted to give you some idea of how they generate power. And I wanted to give you the top 5 issues that we've found. I have investigated approximately 25 solar fires to date, and I would say that 85% of them involve loose connections, and the loose connections themselves, and a lot of it is just it's lost or missed in the commissioning process by the contractor involved. Um, and it is usually a simple find. If you test these systems under load with an IR camera, you'll be able to find them. So if that seems to be they're wanting to throw me out here, I've gone over my hour. I do apologize for that. But I'd like to thank everyone for showing up, and hopefully we can connect in our next show. If you want to download the presentation, you'll see some stuff after this slide. It talks a little bit about more failure mechanisms. And I would like to thank everyone for coming. What I want to do, there's some questions here. I've got some questions. Why do the panels catch fire? The panels themselves, it depends. We find that it's not necessarily the panel that catches fire, it's usually the connector. The connector itself will catch fire usually in the combiner boxes if they're put together loose. We see panel fires in the connection box on the back of it when we have certain maladies that occur, like black backflow of electricity, or we have a failure that's actually what it is. It's a small, what they call diode box, and the diode box it's set into a plastic container, and it will overheat in the back of the panel, and it will catch fire. And the problem with it is when these panels catch fire, or the back of the diode box catches fire, it drips this fire down, and unfortunately, this thing's sitting on top of usually an asphalt bitumen membrane on top of Home Depot, and the asphalt membrane catches fire, and then we've got this thermal event that rapidly grows just simply because you got fire on top of really hard fuel. Um, Basic maintenance. I've got another question about basic maintenance, which is a great question. The O&M maintenance on these things, we see the reputable companies yearly going from system to system, and the initial work that they do on them is an IR scan. We have a division now that's setting up IR scanning done from drones, because we can, to manually scan, say a solar farm would take you a week, where our drone systems now are flying overhead. They're identifying hot spots quickly, and then they're manually investigated from that spot. So that's some of the systems that we're seeing. Obviously, retorque is important, but retorque can be done quickly, simply looking at an IR scan, because that's going to tell us where we have loose connections. Now, as far as IR scanning is concerned, you have to understand that the only way you're going to get a lot of heat buildup is if you have a lot of energy going through the panels. So if it's a cloudy, lousy day, remember we talked earlier, these panels are not going to generate a lot of energy. So you're not going to get a lot of heat buildup. So you want to make sure that if people are doing their IR scans, that they're doing such on a day where they have a lot of energy being generated, and that's the easiest way to find these issues. Um, Bear with me here. Um, I'm looking at my questions. Um, Lots of Jonathan says lots of systems and strings involved in this procedure. Yeah, there's an enormous number of connection points, and that was what I was trying to get at. Is when you have like a simple 2000 panel um, solar array, you've got 2.5 connections, so you're looking at 4,500 or 5,000 connections on one solar array. So there's an enormous amount of failure points that can occur on these systems. Um, and I know that usually when I finish these talks, people say, "Well, I'm not putting those things in my house," and I can understand that if there's no quality assurance and quality control put in place here. Um, so right now, there's a question here: is there a guide requirement for periodic IR scanning? Um, right now, I know that the National Electric Code is looking at several code changes that will include such. They're also looking at safety systems. So if we do have a rooftop fire, what we noticed in Ontario originally was the fire department would show up and they would have no idea what to do. They didn't know, could they put water on it? Could they turn it off? And they would go downstairs and turn off the master switch, but not understanding that they still generated power. How do you attack them? What do you do? And we're seeing that the National Electric Code now is putting systems in place that oh, thank you, slides. They're saying the National Electric Code now is putting systems in place that will automatically shut off the power within a certain radius of the actual array itself. So the fire crews can get to such a distance to the solar array and understand that there's no power there. But from there in, they have to be careful because they still are going to generate power. You cannot shut these things off. Um, so there's one final question here, and it's a little difficult for me to see. Is does Envista uh, bear with me, sorry, folks, a little difficult to see here. Okay, there we go. Does Envista perform, um, or any other company perform inspection services? Yeah, one of our new mandates here is that we're looking at the pre-loss inspections. It's the world that I came from, and I would say within 6 months you're going to see some kind of announcement that comes out of Envista about that very thing. Um, uh, we we uh, we have a very well developed QA/QC program, and we're doing a lot of it in the risk management side of things. And we also, for those that are interested, we can also come and talk to the risk management people and deliver a more elaborate version of this presentation for those that are interested. Um, I have a question from Catherine, and Catherine asks, "What is the lifespan of a panel?" Well, that's very interesting. They're saying the manufacturers are saying that the lifespan of their panels are 20 years, which is an interesting concept in that there's not a panel manufacturer out there right now that's saying that their panels can last 20 years. That's even 20 years old. So we're kind of questioning exactly how the math they've used to be able to develop that. But that is an interesting question. So if a panel does last 20 years, and you put it on a roof that's only going to last 5 years, what's going to happen? And this is an issue now that we have, especially here in Ontario, with a lot of the big box stores where they slap these things on the roof, and now we're starting to see degradation of the rooftops. Because you got to remember that these panels absorb heat, and they still bleed. They're basically great big heat absorbers that transfer a lot of this radiant heat down to the rooftops themselves. And we are seeing some evidence to suggest that there is degradation of the rooftop. Now, that's a whole white paper unto itself, and it's something that's being looked into now. And I know that the solar trade show that's about to happen in September, that there will be some papers presented on that at this stage. But roughly, the lifespan of a panel is about 20 years. Now you have to remember though that the actual panel itself, the modules or the cells, have a degrading lifespan. So they're not, well, they'll generate 100% of their power in the initial year. They won't generate 100% of their power in the second, third, fourth, fifth, and sixth, and you will see a degradation of the amount of energy that's developed from a panel itself. Can panels be mounted on other structures? I guess the question, it's interesting. A panel can be mounted on basically any flat surface. Depending on where you are in the world, and the actual where the sun actually travels and the path it takes from horizon to horizon, the panels will have different slope to them. I know that traditionally in Ontario here we see about a 20-degree slope. Some panels we see at a 5, 10, 20-degree slope. So that allows it to absorb more energy. More towards the equator, we see flatter panels. We see 5-degree slopes because the sun is always higher and you can absorb more energy that way. But when the sun is low in the sky, depending where you are, the panels will change. We didn't talk a lot about what they call tracking panels. We're just talking about rooftops, but they actually have panel systems that are tracked to basically a moving array where the panel will point directly at the sun all day long. The whole array moves with the sun. However, most of these systems are either massive in size in the middle of a desert or small in size. We see a lot of farmers that have these kind of things in farming areas. So it's about 3:10. I've gone about 10 minutes late. If anyone has any questions, on the screen you've got my email address. Feel free to email me, and I'll gladly be willing to talk to you a little bit more about it. I again apologize for rushing through things, but I wish you all the best on your weekend, and thanks very much.
Thanks, Scott, and thank you everyone for joining us today. And our next webinar is going to be July 7th on equipment restoration, so make sure you sign up for that one.